Magnetic fields. Earlier, when we worked with electricity and electric fields, we talked a lot about electric field lines. And basically they were used to show how electric charges would exert forces on other charges. We have a similar concept that's going to be used in magnetism. What's nice about magnetic field lines are that you can see them more easily. For example, over here we have a bar magnet here, and we've labeled this the North Pole and this is the South. And then iron filings were sprinkled about it. And you can see how the iron filings are lining up, and you can see how it goes from north to south, then over here these lines go out, and actually if we had a bigger piece of paper and more iron filings you would see it looping around all like this. So those are what magnetic field lines look like. The iron filings that we sprinkled around the bar magnet here act like little tiny magnets. And what they do is they align with the magnetic fields of the large magnet here. Notice again the field exits one end, goes around, comes back in, and then even look within the magnet here. You can see how the field lines continue right through. So you have a loop here. Magnetic field lines always make loops, unlike electric field lines, which again you could have a positive charge here and a negative charge over here. And the field lines just do this. There's no loop there, okay? Magnetic field lines have to form a complete loop. We're now going to define a direction for magnetic field lines. When we worked with electricity, we said field lines started on a positive charge and terminated on a negative charge. So, since we have a choice of north and south poles, we're going to say that the magnetic field lines leave the North Pole. Again, this is arbitrary, could have been defined the other way, but this is what we're doing. And these lines will specify the direction that a north pole of a magnet will point to. So if I put another magnet in here, like this, it's going to point that way, okay? It's going to point along with the field lines. And again, like electric field lines, the more lines per unit area, the stronger the field. So you can see if I'm at a point over here, I'm not showing any field lines through there. Again, there's obviously an infinite number, but for the purposes of this we show it's pretty empty. Where over here you take this area, you've got a number of magnetic field lines. So what we're representing here is the magnetic field is strongest at the North Pole and the South Pole. So that's very much like the electric field. Denser the lines, a stronger magnetic field. And also, you might say, well, what about this? You told me these guys were all in loops and this is just going off. Well, again, if we were to continue this around, I'm sorry for the uneven circle, that would come around here and would make a complete loop. Starts from the north, makes a loop, comes around to the south. Here's another case. This case, we spin this magnet around, so we have the South Pole facing the North Pole. And we know from our previous discussion that these two magnets are going to attract each other. And look at the difference in the field lines. If you were to put, again, iron filings here or little tiny magnets, they would all line up on this field line, kind of like this. And then here you have your other loops when you're further out. And of course on the other side it doesn't look as it's affected that much by this magnet. Okay, but this loop is going to come around. And again, not terminate right away on this guy, but come and join this guy over here. It'll then come out, go through, and just complete the loop. I should probably just finish that there. So once more, just to emphasize the fact, all magnetic field lines form a loop. Here's the biggest bar magnet of all, the Earth. The Earth's magnetic field is very similar to that generated by a bar magnet. It's caused by the circulation of molten iron alloys in the Earth's outer core. Now, many people are still working on that. We're not exactly sure because iron, when you melt it at the incredibly high temperatures it is inside the Earth's core, it's not magnetic anymore. However, there are currents being generated down there, and later on we'll see how currents can generate a magnetic field. So really, this can be worked on by many of you when you go to college or grad school and figure out exactly where the magnetic field comes from. An interesting point is the Earth's North Pole, the geographic North Pole, is really a south magnetic pole. Because whenever you have a magnet, which way does it point? Well, it points up to the North Pole, which means that the magnetic field lines are coming from the bottom, from the South Pole, the Earth's geographic South Pole, going up this way, and you can see the magnet here aligning with it, and coming into the Earth's North Pole. So really, the Earth's geographic North Pole is its magnetic South Pole. Now, it's not exactly at true north, which is what the Earth revolves around. It's shifted a little bit, and they call that declination. So the magnetic pole is on this line here, and the actual rotation axis is here. Now, that's going to be important if you've ever using compasses in the woods, or you're on a ship where you have a gyroscope that tells you the true north. The magnetic north is just a little bit off. The magnetic field of the Earth extends from the core of the Earth all the way to the outer limits of the atmosphere, and in a region that's called the magnetosphere. This is a very cool picture, obviously not drawn to scale. This is the Sun, and this little guy right here is the Earth. And these lines here show the interaction of the solar wind, and the solar wind is protons, electrons, and other ions that are shot off by the Sun continually, and they bombard the Earth. Now, the great thing about our magnetic field is it protects us from all those ions. They hit the magnetic field, they lose energy, and they don't come and strike the rest of us. And there's some theories that the reason Mars, for example, has no atmosphere, it has a very weak magnetic field, and it was not able to protect the planet from the Sun's solar wind.